Hi, this is Kyle, and in this video we're going to look at C++ built-in arrays. You might also hear them called C-style arrays because they do come from the C language, and it's worthwhile differentiating between C-style arrays and C++'s array class from the standard library. C-style arrays are a lot more rudimentary in nature, so let's take a look. Alright, I've got a C++ code skeleton here. This could just as easily be a C code skeleton, and the only thing you'd have to change would be the way I output things here, and potentially the way I do the for loop. Everything else will work the same between C and C++. So to create a new array, I just have to describe the type. So this will be an array of ints, and I need a variable name, and I need to specify the size, optionally depending on how you initialize it. So here, my array 5 specifies that I want 5 ints in this array. And if I want to access that array, I can use the traditional notation using a for loop. I did ++I, you could just as easily do I++. And I'll output my array at I. Now, if you've ever done any programming with arrays before, especially in Java, this notation should be very familiar to you. Now, what I have right here, I didn't initialize it, so if I printed this out, I would just get a bunch of garbage. But I can actually initialize it using this notation here. So I have a few elements in there, and let's just run this to make sure we're up and running here. All right, I see 11 through 15, just like I expected. Now I'm curious, let's print out what my array itself holds, because my array is a variable. It's an array variable. Let's see what happens if we print that out. Just my array by itself. And out of curiosity, let's also print out the different addresses of these variables. So I'm printing out what's stored in my array, and I'm printing out the address of each element. So this is an element of the array, my array at I, and if I put the address of operator in front of it, it'll get the memory address. So let's run that. And I get a bunch of memory addresses here. Now I expected that for all of these because I specifically asked for the address of, but when I printed out my array, you may not have expected to get an address. Well, that's actually just how it works. When you create an array variable, you can use that array variable to act like the address of the very first element. So see that? Those match. That's the address of the first element, and that's the array variable that we used. So to draw this out, it might look something like this. So my array, well, let's see what the addresses were. And notice these are all spaced 4 bytes apart. That's because on my system, integers are 4 bytes long. So let's see, F8, FC, F8, FC, then I had 00, 04, 08. And you're going to get different addresses each time you run this, most likely, and especially on different systems. So at F8, I had 11, FC 12, 13, 14, and 15. And also, we noticed that my array holds the address of the first element. So I can sort of treat it like a pointer. Now, if it's a pointer, I should be able to dereference it, right? So let's try that. Let's see what we get. And I'm going to wipe out this loop here. And instead of my array, I'm going to do star my array, because star is the dereference operator, and it should actually go to that address. Now let's see what we should expect here. Normally my array would be the address, F8, but if I say star my array, it should actually go to F8 and get this value. So I should be able to get 11 here. Let's verify. Sure enough, I got 11. Now, we also have this thing called pointer arithmetic. And essentially, we can do math with pointers. So here, if I wanted to get to the second address, let's see what we would do. It looks like I could just add 4 to the memory address and then dereference it, and I should be at the next address. Well, when you have a typed pointer like this, it's essentially a pointer to an int. When you add 1, it'll automatically jump up 4 memory addresses because it knows that you are working with ints. So if you add 1, you really mean the next element. So let's see what happens. Well, first off, let's check the difference between myArray and myArray plus 1. And these should both be memory addresses. So myArray should be one address and myArray plus 1 should be another. And sure enough, when we added 1, we got a difference of 4. So if you can count in hexadecimal, see C, see D, E, F, and then we're at D0. So that's a difference of 4 there. All right, so we should also be able to dereference myArray plus 1. So let's dereference both of these. And I can't just do this because it will dereference it first. We actually need to put this in parentheses so that I make sure I add 1 to the address and then dereference it. So let's compile this and try that out again. Okay, so I get 11 and 12. So what happened here when I added 1, so I added 1 to the memory address. It actually moved down here. So myArray added 1, and then I said dereference, and then that actually took me in here and got the value of 12. So it looks like we can actually use pointers instead of array notation. And that's exactly true. So whenever I use pointer notation or array notation, I can always use the other here. So let's try and decide exactly what the equivalent would be. So we'll do myArray at 1, for example. Or let's see, myArray plus 1. Since we just had that, we know the equivalent of that from array notation should be, if we wanted to access element 1, which is 11, I could just say that, right? So these 2 lines should print the exact same thing. And I actually made a mistake here. I should have said myArray plus 1 with parentheses here. Well, okay, so element 1 had 12, not 11. And this applies to pretty much any array element. So whenever you use this notation, you can use this notation. And likewise, when I did 0, I didn't have to add anything, but that's sort of the same as saying myArray plus 0. So you can just dereference it, or you can add 0, and I should be able to get the same thing. Nice. All right, so just one final test. Let's try doing that for loop again, but this time let's use pointer notation as an iterator instead of using the array notation. So actually, because I'm going to actually mess with this pointer, I'm going to create another value called myArray pointer, or I'll call it myArray iter because it's an iterator. And I'm actually going to make this a pointer, so it points to somewhere in the array. And I can set it equal to myArray, since we know myArray has the address of the first element. All right, so I can use the same loop here. And now I could just simply replace myArray bracket I. I could have replaced this with myArray plus I, put it in parentheses, and I could also dereference that. And that would be the exact same thing as saying myArray at I. So again, those two are the same thing, but here I'm actually going to modify my iterator. So I'm going to first print out star myArray iter, and that should get the first element. And then after that, I can just say my array iter plus plus to increment that. Of course, since I'm only doing that on this line, I can put that beforehand. Or if I want it to be really concise, I could just say plus plus here, and that will increment the this will increment my array iter. It'll actually change this pointer after it's been dereferenced. So I'll get the first element and then it'll increment this. And keep in mind, by doing this, I'm actually changing my array iter. I'm actually changing what it points to. So I wouldn't want to do this to the original array variable, because then I would lose the beginning of the array, or else I'd have to rewind it or something. So let's try running this, and this should also print out all the array elements. Nice. So that's the gist of C-style arrays. To recap, C-style arrays are allocated in a contiguous block of memory. So each element comes right after the next in memory. And the array variable itself is a pointer to the first element. So we can use pointer notation and pointer arithmetic to move through the array. So I hope this has been informative, and have a good one.